Hello there, Mr. Sutton here, bringing you the Algebra 2 7-2 lesson on graphing rational functions. This is going to be a two-parter. In part one of this, we're going to be graphing transformations of rational functions, and then we're going to move on from there to find asymptotes of rational functions based off the functions themselves, and we're going to use that to do a little bit more graphing. And then as an add-on to that, if you're doing the honors version of this, we'll also be rewriting rational functions using a little long division. And we'll see a cool application at the end involving some 3D printed hands. Let's go. To start things off, we're going to define what we mean by a rational function. So rational has the word ratio in it, and in fact, a rational function is a ratio or quotient or division of two polynomials. So kind of the general form of all the rational functions is f of x equals p of x over q of x, where p and q are both polynomials. Now it is important to note, since some polynomials can also be constants, that we're not allowing that in the denominator. There has to be a variable in the denominator. This q of x needs to have some kind of x in it in order for this to be considered a rational function. And also by extension, we can't have 0 in the denominator, but that's already kind of eliminated by having a variable in there instead of a constant. So there is one other form that we'll be looking at in this lesson, and that is what I like to call the transformation form, for lack of a better term. And it's this form a over x minus h plus k. This is kind of like the vertex form of rational functions, where this allows you to easily shift and translate and transform things, which we'll be doing in a little bit later on in this lesson. But for now, let's focus on the simplest rational function out there. Take a moment, pause the video, and go ahead on Desmos and graph out 1 over x and see what you get. So here we are on Desmos. Let me do f of x equals 1 divided by x and see what this looks like. All right, so it looks like we've kind of got these two sort of branches, and I'm wondering if these end up crossing either axis. So let's zoom out a little bit. Let's just keep zooming out. It's kind of hard to tell. They look like they're touching the axis. Let me zoom in instead. And let me just start kind of moving along this and seeing if we ever touch. So it's looking like if I zoom in far enough, I'm getting closer and closer, but never actually touching the y-axis. Now if I go back home and check this out on the x-axis, let me just go along a long ways here. If we zoom in close enough on this, we notice that, yeah, we're not touching that axis either. So here's a basic sense of what this looks like. We've got two different branches, and this is actually called a hyperbola. That's when you have two symmetrical branches, and you also have branches that are approaching these two asymptotes. Now, you might wonder, where are the vertical and horizontal asymptote? I don't see any dashed lines on here. Well, if the x and y axis are the asymptotes, then we're not going to draw them. But if you wanted to draw them, you could kind of draw them if you were able to, maybe a different color ink on top of the x and y axis. So let's talk a little bit more about the parent function for these rational functions. So the parent function is 1 over x, and there's a parent table that goes with this. It turns out you can actually graph these, at least in this transformational form, if you have 2 points on either side of the vertical asymptote and you know both of the asymptotes. So if you have those 4 pieces, you can always graph these. The easiest 2 points to get, on the left side, the parent function has -1, -1. And on the right side, we've got 1, 1. So this will be our parent table whenever we have to graph these things. It's also worth noting that the parent function has the vertical asymptote x equals 0. And I'm going to be calling these VAs for short because that's a lot to write out. Now, because we have a vertical asymptote there, that means the domain of the parent function is going to be x not equal to 0, because we can never touch that vertical asymptote. And for the horizontal asymptote on the parent function, we have the line y equals 0. And I'll call horizontal asymptote ha for short, because that's kind of funny. Now, because we are getting closer and closer and never touching that horizontal asymptote, the range of the parent function is going to be y not equal to 0. Now, it is worth noting that the domain of any rational function is going to exclude where these vertical asymptotes are. These asymptotes, though, are a little bit different from the horizontal asymptotes. A vertical asymptote is caused by essentially trying to divide your fraction here by 0. So you'll never be able to do that. That's always going to be undefined. The horizontal asymptote is caused by something different. This is caused by plugging in very large or very negative values for x. As you plug in bigger and bigger and bigger values for x, this fraction gets smaller and smaller and smaller and smaller because your denominator keeps growing, but you can never quite get to 0 because you don't have 0 in the numerator. So it's long-run behavior giving us the horizontal asymptote, short range giving us the vertical asymptote, with the curious result that if we were doing more complex rational functions, there are some that actually do cross their horizontal asymptotes, but never the vertical ones. Anyway, in this lesson, we're going to confine our problems to linear numerators and denominators, so we don't have to worry about any of that this time around. So now that we have a sense for the parent function, this 1 over x rational function, we're going to see what happens if we do a few transformations on that, like this g of x equals 3 over x. So our basic strategy, just like when we're doing any kind of transformation, is we're going to write out our parent table and then use our transformation rules based on what we see in the new function to change the x and y values. In some cases, we'll be multiplying x or y by a number, in some cases adding or subtracting. So all of those things we've done before. There are a few minor differences, though, that are kind of important when we're dealing with rational functions. For one thing, whenever we're dealing with x and y's, we're always thinking of inside versus outside the original function. Well, what does that mean in this situation? Inside the function for a rational function means inside the denominator. The denominator counts as the inside of the function. So anything that happens in our denominator is affecting the x values. Outside is going to be everything else. And by everything else, literally everything else. So the numerator, that counts as outside. Things that are being added or subtracted outside the whole fraction also count as outside, and those sorts of things are going to affect the y values, and they're going to be exactly what they look like, whereas the inside stuff is going to be opposite of what it looks like. And there is one more little thing to talk about here. Normally we would just be affecting the points and redrawing the points and going through those, but since these graphs also have asymptotes, we're going to redraw the asymptotes as well. And eventually we're going to be going through our points and approaching the asymptotes to graph this. So pause the video, see if you can figure out what type of transformation this is, and see if you can modify the parent table and regraph this thing. All right, since we have a 3 being multiplied by, there's kind of an invisible 1 in the numerator, this counts as a vertical stretch. And for our parent function, again, the table we're going to have -1, -1, and 1, 1, so pretty easy parent table to remember. Now, since there's nothing new happening inside the denominator, we don't have any changes to x. So I'm just going to rewrite all the x values when I graph out this g function. But now for the y values, since we have this times 3 up here in the numerator, that's going to be multiplying 3 times the y values. So 3y is what that looks like. So for my x's, I've still got -1 and 1. For the y values, now I've got 3 times -1, so -3, and then +3. And for my asymptotes, since I didn't shift this thing at all, I've still got x equals 0 for the vertical asymptote and y equals 0 for the horizontal asymptote. So let's graph all this out. So for my asymptotes, I've got, again, 0 and 0. There's no need to actually graph these since we have the x and the y-axis here already as kind of guiding lines for our graph, but I'll just draw a little dashed line over the y-axis and the x-axis just to really hammer home the point that we do have asymptotes there. And we'll just graph our 2 points now. We've got -1, -3, which is right here, and then 1, 3, which is up here. So again, we're just going to approach the asymptotes and go through the point. So here's our first branch down there. And for our second branch, we're going to be coming from up above here near the y-axis and ending close to the x-axis, so sort of like this. And we really only do need 1 point over here. The asymptotes guide all the behavior of this thing otherwise. We're going to do another example now. This time around, not only are we graphing this, but they also want us to figure out the domain and the range, which is one little extra step. So before we really dive into this thing, take a quick moment and see if you can figure out what these transformations are doing to the graph. All right, so we have this x minus 4. Since denominator counts as inside, this is a horizontal change, and it's opposite of what it looks like. So we're actually translating 4 to the right. And then this minus 1 outside is going to be a vertical change. We're going to be shifting down 1. So right 4 and down 1. So one thing to keep in mind when you're doing these transformations is that translations in particular are also going to shift your asymptotes. Everything is going to shift, including kind of the center of the graph. Since you're shifting your asymptotes, that means you're also going to be changing your domain and your range. So take that into account when you're figuring out the new domain and the range. It's not going to be the same as the parent function. So with that in mind, pause the video and see if you can make all this happen. All right, so just like before, let's write out our parent table. We have -1, -1, and 1, 1. And for my g function now, changing my x and y values, since I'm going right 4, I'm going to use x plus 4 as my new rule. Since I'm going down 1, I'm going to have y minus 1. So we've got -1 plus 4 is going to be now 3. 1 plus 4 is 5. And then over here we have -1 minus 1 is -2. And 1 minus 1 is 0. Now again, we also have to change our asymptotes because of the shifting. So since I'm adding 4 to all the x values, the asymptote at x equals 0 is now going to be at x equals 4. And since I'm shifting down 1, the asymptote that used to be y equals 0 is now going to be y equals -1. So let's go ahead and graph all this. So we've got, let's see here, x equals 4, my vertical asymptote's right there. And now let me graph y equals -1, the horizontal asymptote. And my 2 points, we have 3, -2, which is right down here. And 5, 0 is right up here. And then the branches going through those points on either side of my asymptote. Oh yeah, I also have to remember the domain and the range. The domain, we can see that we're not touching x equals 4. It matches the vertical asymptote. So we're going to write x does not equal 4 for domain. And for range, we'll have y does not equal -1. Just to make sure we've really got this and can handle anything, we're going to do one more example. This one's got a little bit more going on in it now. Pause the video and see if you can figure out what's going on and what that new graph should look like. All right, so kind of laying out the transformations that are happening. This -4 up in the numerator is doing two things. The negative up here is giving us a vertical reflection, and the -4 is giving us a vertical stretch. We also have translations going on. We have a shift of left 2 because of the +2 down here, and down 1 because of the -1 out there. So just to rehash all that, we have a vertical stretch and a reflection, and we have a translation left 2 and down 1. All right, so here is our parent table, -1, -1, 1, 1, and the g function now. The only thing happening horizontally is the stuff down here in the denominator. Left 2 means we've got x minus 2, and that's it for the x's. But now for the y values, the stretch and the reflection mean we have to multiply our y values by -4, and then afterwards we also have to subtract 1. So -4y minus 1 is what that rule looks like for this one. Let me go ahead and change those 2 points now. We have, let's see, -1 minus 2 is -3. 1 minus 2 is -1. And then -4 times -1 is 4. Minus 1 is 3. -4 times 1 is -4. -4 minus 1 is -5. For the new horizontal asymptote, we shifted left 2, so we have x equals -2 for that. For the new vertical, or for the new horizontal asymptote, so this was the vertical asymptote, for the horizontal asymptote, we only shifted down by 1, so that's the only thing changing for that one. We're going to just have y equals -1. All right, here's my graph for all of this stuff. So let's see, since I'm going from -5 to 3, I'm going to leave myself a little extra space on the y-axis. So I have my vertical asymptote at x equals -2 right here. And now the horizontal at y equals -1, which is right about here, halfway between 0 and -2. We have the point -3, 3, so back 3, up 3 is right there. And we also have -1, -5. So left 1 down 5 is right there. Here's one branch going through that point on the left. Here's the other branch going through this point on the right. And the new domain, we're going to have x does not equal -2, just like the vertical asymptote. And for the range, y does not equal -1, just like the horizontal asymptote. So this is the end of part 1. Feel free to pause the video and do some practice problems with this transformational form here, and then rejoin us when we talk about graphing things that are in a different form of rational functions. See you then. Welcome back. You're rejoining us for part 2 of graphing rational functions. In this one, we're going to move away from that transformational form and talk about graphing things in something I like to call the general linear form. That's not the official name, but here's what I mean by this. We basically have something in the form of ax plus b over cx plus d. We essentially have the general form, but more specifically, we have a line divided by a line. And that's really as far as we're going to go in terms of the crazy complexity of the rational functions we're dealing with, even though that these could be quadratics or even higher. So how can we graph something in this form? The key is we're going to find some vertical and horizontal asymptotes that we can use as sort of guidelines, and then we'll plug in a couple x values and get some points to go with those. But first we have to figure out how to find the asymptotes from something that's in this form. So with vertical asymptotes, as we talked about in the last part, those are happening where your denominator equals 0. Those are caused by the attempt at dividing by 0, which is always going to be a failed attempt. So if you want to find the vertical asymptote for something in this form, you just need to set this denominator, cx plus d, whatever that actually is, whatever c and d really are, you just need to set that equal to 0, and then solve for x. So in this case, we could subtract d and divide by c and get -d over c. And that gives you kind of a general formula for the vertical asymptote for something in this form. But if you forget this little formula, you can always just set the denominator equal to 0 and solve for x. So that takes care of vertical asymptotes. Horizontal asymptotes, we spoke briefly about those. Those are caused by something different. Those are caused, in theory, by x approaching positive or negative infinity. Those are essentially when you're going to the far right or the far left of the graph, the y value that you're tending towards. Now, how can we possibly figure something like that out? I mean, you can't really plug infinity in, right? Well, we can't, but we can plug in very large x values either in the positive or negative direction and see what happens. In fact, we're going to go on Desmos and do just that. So here I am on Desmos. I'm going to create a function that's in this general form, but I'm going to have to put some numbers in there. So let me do f of x equals fraction. Let me see. Let's do 2x minus 8 over, I don't know, 4x plus 20. Okay, and it's a vaguely rational function looking sort of graph. So the real question I'm wondering, though, is what happens if I start plugging really positive or really negative x values into this thing? So let me start by plugging in some positive x values, like f of 10. And that comes out to 0.2. Okay, how about f of 100? Well, that is a little bit more. It's about 0.45. F of 1,000. That's really close to 0.5. How about f of 10,000? 100,000. 1 million. 10 million. There's a pattern here, right? We are getting closer and closer to 0.5. And what if I make this very negative? Well, at a very negative value, we're still very close to 0.5, although kind of coming from the other direction. So what's going on with this? Well, here's another experiment. Let's see what would happen if I change this -8 to a negative 8,000. So we're still very close to about 0.5. So changing this number didn't really affect things. What if I change this 2 to a 1? Well, now we're very close to about 0.25. What if I reverse it and make this 4x over 1x? Now we're very close to 4. So what's going on here, just to kind of summarize this, is that as you plug in very positive or negative x values, this first term in each side is getting very big compared to this other constant that's not growing at all. At very large x values, this b and this d basically can be ignored. They become insignificant. And all you're left with is ax over cx. And if you just cancel out those x's, we see that this thing is just going to end up approaching the ratio of the lead coefficients. That's what our horizontal asymptote is going to be. So if you like formulas, if you have something in this form, you could say that your horizontal asymptote is just going to be a over c. Now, this is making the assumption that these are just both first power, or at least have the same exponent. It actually works even if these have different exponents as long as it's the same exponent on the top and the bottom, like x squared over x squared. But this is something we can use right away to get our horizontal asymptote. Now that we've talked a bit about finding vertical and horizontal asymptotes, here's a function in general linear form. Pause the video and see if you can figure out the asymptotes, both vertical and horizontal, from your denominator and from your lead coefficients. Pause the videos, see what the VA and the HA are on this one. So for the vertical asymptote, we have x plus 5 equaling 0 is kind of a starting point. And then solving for x, we get x equals negative 5. So that's our vertical asymptote. For the horizontal asymptote, again, we're taking the ratio of the lead coefficients. So we've got a negative 1 for this negative x up here, and a positive 1 for the x down here. So that's negative 1 over positive 1, which we can reduce to y equals negative 1. So those are our asymptotes. We also need some points. We need 2 points, one on each side of the vertical asymptote in order to graph this. So to make that happen, you're just going to plug in an x value on either side of that vertical asymptote, and that'll get you 2 additional points that you can then plot on your graph and use that to graph it. Now, before you pause the video, one quick recommendation. I would highly recommend you pick x values that are very close to this vertical asymptote, maybe one to the left and one to the right. But that's just my recommendation. Pause the video and see where that takes you. All right, for my first point, I'm going to plug in something a little bit to the left of this at negative 6. So if I plug negative 6 into this function, I've got negative 6 minus 1, so that's 6 minus 1, which is 5, over negative 1 reduces to negative 5. And feel free to do this on Desmos if you want to be extra careful about the number crunching here. Now let me also pick an x value to the right of negative 5. I'm going to go with negative 4. So if I plug negative 4 into this function, now I've got 4 minus 1 over negative, or positive 1 rather. So that's going to be 3 over 1, or just 3. So putting all this together on a graph, I've got the vertical asymptote at x equals negative 5, and that's, by the way, why my graph has shifted so much to the left here, so I can accommodate that. So we've got negative 5 for the vertical asymptote, horizontal asymptote at y equals negative 1, right about there. We've got the point negative 6 comma negative 5, which is right down here. And we also have the point negative 4 comma 3, which is going to be right up here. So here's one branch going through that point, and my upper right branch going through that other point. They did want the domain and range on this one. The domain we can see from the vertical asymptote is x equals, or x does not equal negative 5, and for the range we have y does not equal negative 1. So just to make sure that we've got the hang of this new process, pause the video and try this next example from start to finish. Same kind of problem as the last one, just some different numbers. All right, just like before, because this is in our general linear form, we're going to start by finding our asymptotes. So our vertical asymptote is wherever x minus 3 equals 0, which is going to happen at x equals 3. For the horizontal asymptote, ratio of the lead coefficients, so we've got 2 over 1, which comes out to 2. And for our additional points, we need 1 to the left and 1 to the right of x equals 3. So I'm going to plug 2 in. That'll give me my left point. So f of 2, that'll be 2 times 2 plus 1 over 2 minus 3, which comes out to, let's see, 5 over negative 1, so negative 5. And then I need an x value to the right of x equals 3. So how about 4? Let's do f of 4. 2 times 4 plus 1 is going to be 9. 4 minus 3 is 1. So that comes out to a total of 9. And then graphing all that out, I've got my vertical asymptote now at x equals 3, horizontal at y equals 2. I have my point on the left is at 2 comma negative 5, which is right about here. And we also have 4 comma 9 on the right side, which is up here. So here's our first branch, and here's our second branch. The domain, we're going to have x not equaling 3, and the range, y does not equal 2. So if you're taking this as part of the CP non-honors part of the course, then this is actually the end of the lesson for you. You can pause or end the video and do some of these problems in this general linear form. If you're doing the honors, then we've got some more fun in store, including a way to rewrite this so that you can use that transformation form, and also a practical application involving some prosthetic limbs. Stay tuned for that. So for the first of our 2 honors parts of this lesson, we're going to be rewriting the function that we just gave you in example 5 in a different form, the form a over x minus h plus k, which is essentially transformation form, and then graph it and describe it as a transformation. So the whole trick behind this, it turns out, is to just use long division to change the form. So basically do 2x plus 1 divided by x minus 3, long division style, and then whatever that comes out to is going to be in this form. So pause the video and see if you can turn it into that form. All right, so with long division, again, you're doing lead term into lead term. 2x divided by x is 2, which we'll put up there above the ones column, the constants column. And then we multiply that back out by the divisor. So 2 times x is 2x. 2 times negative 3 is negative 6. And then we have to subtract all that. 2x minus 2x is 0. That cancels. And we have 1 minus negative 6. Careful with those double negatives. That's actually 1 plus 6, which is 7. So 7 is our remainder. Normally, we would rewrite this as 2 plus the remainder over the divisor, so 2 plus 7 over x minus 3. But because they want it in this form, we're going to write the 7 over x minus 3 first, and we're going to put this quotient of 2 afterwards, and that'll actually end up being our k value. So the a value ends up being the remainder. The divisor is your denominator, and then your k value ends up being your quotient, is the way this always works out. So this is now just that transformation form. Pause the video, take a moment, and just finish graphing this thing out. All right, so transformation's going on here. The 7 up here gives us a vertical stretch, and the minus 3 and the plus 2 gives us a shift 3 to the right and 2 up. So we've got our parent table, negative 1, and 1, 1. And now the g function, we're going to have for the new x rule, we're going right 3, so x plus 3. For the y rule, we're multiplying by 7 and then adding 2, so 7y plus 2. So our new x values, we're going to have positive 2 and positive 4. For the y values, we have negative 7 plus 2, which is negative 5, and 7 plus 2, which is 9. Graphing all that out, asymptotes. New asymptote, we're adding 3 to x, so we have x equals 3 for the vertical asymptote, and we're shifting up 2, so our new horizontal asymptote is going to be y equals 2. So putting all that on our graph, here's our vertical asymptote at 3, horizontal asymptote at 2. We have the point 2, comma, negative 5, which is right there, and 4, comma, 9, which is all the way up here. And then here's the first branch and the second branch. Now the neat thing, if you look back at what we got for our last problem, here was the doing this example a different way. We end up with the same thing. So here was what we had before using the old method, and here's using this rewriting it method, same exact asymptotes, and honestly, if you look at the points, this is 2 comma negative 5. That's the one of the point we got, and 4 comma 9. Now we just happened to pick x values that were 1 away, which is another reason for doing the 1 away, is it's going to match your parent table kind of anyway. But yeah, it all works out, so that's pretty neat. For our final problem, we're going to do a little real-life application here. So we have a 3D printer building objects by depositing material one layer at a time, and the layers are bonded together, creating a solid object, like this hand here. Let's say we have a medical researcher making these prosthetic hands using a printer. The printer, they're saying, costs $1,000 and the material for each hand is $50. They want to know two things. How many prosthetic hands have to be printed for the average cost to fall to $90? And what happens to the average cost as more of these are printed? So for average cost, just to get a formula we can use, that's going to be the total cost of all the hands divided by the number of hands. So that's sort of our average here. And just to kind of try to set this up, our total cost has two components, right? We have this $1,000 startup cost, and then we have $50 for each of the hands. So if we think of this as a function in terms of x hands, 50x gives us the total cost of all the hand material. So we have to do 1,000 plus 50x. And the number of units, the number of hands, is just going to be x. So this is our average formula. Pause the video and see if you can figure out what x needs to be in order to make this whole thing come out to 90. All right, so we're going to set 90 equal to all this. And to solve for x, one thing that would be helpful would be getting x out of the denominator, which I can do if I multiply both sides by x. So this will give us 90x equals 1,000 plus 50x. And then if we subtract 50x over here, we have 40x equals 1,000. And then 1,000 divided by 40 is just going to be, well, let's see here. If I had 100 divided by 4, that would be 25. So 25 hands will give us the average we're looking for. Now, how about this other one? What happens to our average cost as more of these are printed? We're essentially asking if x approaches infinity, what does the average cost become? Well, we're essentially asking for the horizontal asymptote. Pause the video and see if you can find the horizontal asymptote for this thing. All right, so using our x coefficients, 50x would be the lead coefficient if we wrote this in order. We end up with 50 over 1 for our horizontal asymptote, or just 50. So this is saying that as you print more and more hands, your average cost is approaching $50 per hand. So that is it for this marathon lesson on rational functions. If you made it this far, give yourself a hand. Until next time, Mr. Sutton signing off.